Okay, college algebra students, what we're going to learn is a new function. What we're going to find is that this function that we're going to be working with is actually an inverse. So let's do a little bit of groundwork. Let me do some explanation, and then I'll introduce you to the notation and the inverse function itself. But to begin with, here's a graph of f of x equals 2 to the x power. So a classic exponential growth situation. What I want you, we've talked a lot about its domain, its range, some of its behavior, but one of the things that's really important is that it's actually a one-to-one function. It passes the vertical line test, making it a function, and it passes the horizontal line test. I know it gets a little tricky in here, but remember these are getting smaller and smaller and smaller. So 1x is actually creating 1y, and 1y is actually goes back to 1x, even though it looks a little shady here, but it's because it's so small. So we are dealing with a one-to-one function. That's important because what do we know about one-to-one functions? We know that their inverses actually exist. So let's investigate that in terms of just a graph. So on this graph, some of the data points that are on this graph for f of x equals 2 to the x, right? We have the infamous 0, 1, right? At negative 1, we're at a half. At positive 1, we are at 2, right? And if you want to do a couple more, at 2, we are at 4, and at negative 2, we are at 1/4. So what that means is whatever this inverse is, right, the data points on the inverse graph are essentially all of those points reversed. Okay, so that would be the data points on the inverse. We know it exists using what we learned about an inverse. This is what's supposed to happen. So when I go plot these points, let me put it in red. We get 4 2's on the graph, 2 1 is on the graph, 1 0 is on the graph, 1/2 negative 1, and 1/4 negative 2. So the behavior of this, right, it's going to be hugging along the y-axis, if you would, and it's going to be steadily increasing up. And that's a classic case because if we drew the line y equals x right here, right, that's the line y equals x, they're supposed to be reflections of each other. So up here in black, this is 2 to the x, right, f of x equals 2 to the x, and down here in red, there's the picture of the inverse function. So we know it exists. I have a picture for it, right? So let's go find it, right? What is this inverse? Well, when we go through what we learned earlier, right, the way that we find the inverse is it begins by replacing the f of x with y, right? And then our next move is to basically interchange the roles. I think I even change colors. Where I see a y, I replace it with x, and where I see an x, I replace it with y. So here, right, is the inverse equation that I am seeing right there, right? You can even check it. If y is equal to 0, right, then x is equal to 1. If y is equal to 1, then x is equal to 2. So it satisfies all the solution points on this, but we have a problem, right? Because what we now have to do is solve for y. And it turns out that no matter what we do, there is no algebraic way to solve for y. The algebra just breaks down in all kinds of ways, because the idea, the y that I'm trying to find is actually up here in an exponent. And so, we can take a y-th root, but we're gonna have a y x over here. It's just, it's algebraically impossible. So here's the dilemma we're in then, right? So algebraically, there's no way to solve for y so that I exclusively know what the inverse function is, but I do know that in fact it exists. I see it. It's supposed to exist by all the theory. So here is what happened. Because of this, we know the function exists. We created a notation, and we justified it using a lot of other math, some calculus, and some other good stuff. But notationally, what we say is if I have the exponential function f of x equals 2 to the x, its inverse is what we call the logarithmic function, and it's defined to be log base 2 of x. So the base of the logarithm is written right below. It's the subscript of the g, and that right there matches the base of the exponent that I have right here. So this graph has the data point 0, 1, 1, 2, 4, 2, and this graph, right, this is the guy that has the data point 4, 2, 2, 1, and 1, 0. And so it's basically a notation. It's a definition. So there's really nothing to prove here, if you would. My proof is behind the fact that I know it exists. I see it. We physically can draw it. I physically can see it. But I can't algebraically solve for it using what we learned back in 6.2. So what we do is we invent a notation. And this notation is famously known as the logarithmic function. So log base 2 of x serves as the inverse of 2 to the x, and vice versa. These are the two functions that if I start with an x, right, the exponential function will take it here, and the log base 2 of x takes a y value here and maps it back. All right, so it's basically the complete circle. I go here and I come back here using that. So those are the two functions that basically reverse themselves. All right, and that has some huge ramifications because we know that they're, if we were to compose them, right, if I took f and composed it with the inverse, right, we're supposed to get x. Or if I took the inverse and composed it with f, I would get x. But we'll talk a little bit more about that in 6.5. Right now, I just want to introduce you to, we do know that an inverse function exists. It's algebraically hard to solve it, so we invented a notation. So when you see a logarithm, like I have here, right, what you're thinking is, hey, this is the inverse of whatever base I have. And so let's go investigate that. We're going to see that this basic shape that we have for log base 2 of x, right, seems to be the basic shape for a lot of exponential growth functions. So let's go investigate that now that we've introduced ourselves to the notation and build from there. All right, see you guys in the next video.